Here is one more example for angular momentum. A 0.005 kilogram bullet traveling horizontally with speed 1 times 10 to 3 meters per second strikes an 18 kilograms door embedding itself 10 centimeters from the side opposite the hinges as shown in the figure. The 1 meter wide door is free to swing on its frictionless hinges. Before it hits the door, does the bullet have angular momentum relative to the door's axis of rotation? If so, evaluate this angular momentum. If not, explain why there is no angular momentum. Is the mechanical energy of the bullet door system constant during the collision? Answer without doing a calculation. At what angular speed does the door swing open immediately after the collision? Calculate the total energy of the bullet door system and determine whether it is less than or equal to the kinetic energy of the bullet before the collision. Okay, so let me call this mass of the bullet m. So this is small m. This hinge has a mass m, length capital L, and it's stated in the problem that there is a distance of 10 centimeters to the side opposite the hinges. So this is the distance r, and therefore I have a distance L minus r between the hinge and the point where the bullet hits the door. So this is going to be L minus r. All right, so what will happen in this situation? Because the bullet will get embedded inside, so when it hits the door, it's going to get embedded inside. So let's draw this. So what will happen is the bullet will get embedded inside, and because the door is pivoted here, the whole thing will start swinging with respect to this pivot point. Okay. Now, the first question is, does this bullet have angular momentum before it hits the door? Okay, so for angular momentum, here is the point, the axis of rotation with respect to which I'm going to try to calculate angular momentum. I can find the position of the bullet just before it hits the door. So let's say it will be here. This will be the r vector, and I see that the bullet just before it hits the door will have an linear momentum vector that's going to be equal to m times v. So I can see that there has to be an angular momentum, because angular momentum is r cross with mv. So I will find out that there has to be an angular momentum of the bullet with respect to the door's axis of rotation. So yes, the bullet has an angular momentum relative to door's axis of rotation before it hits the door. And part B is asking me how much is that angular momentum. Well, the angular momentum L is equal to R cross with mv. So first of all, let's think about the direction of this angular momentum. So if I have this is my x-axis, this is my y-axis, and the z-axis is coming out like this. So this is x, this is y, this is z. I will find that the angular momentum from r cross mv should be in k-hat direction, because when I curl my fingers pointing from the hinge to the point of application of the impulse and curl my fingers towards the linear momentum, the thumb points in plus k-hat direction. So there will be an angular momentum in plus k-hat direction. And what is its magnitude? The magnitude of the angular momentum will be the length of this vector r, which is L minus r, times mass of the bullet times its velocity v. So this is going to be, it's a 1 meter wide door, so it's 1 meter, 10 centimeter from the opposite side, so minus 0.1 meter. Mass of the bullet is 0.005 kilograms. Velocity is 1 times 10 to 3 meters per second. So I'm going to get here 0.9 times 0.005 times 10 to 3. So this will be 4.5 kilograms meters squared per second. And what is the direction? In k-hat direction. So this will be the angular momentum of the bullet just before it hits the door. Is the mechanical energy of the bullet door system constant during the collision? And I want to answer this question without doing any calculations. Since the bullet gets embedded inside the door, the collision is inelastic, and therefore the kinetic energy is not conserved. Okay, so the mechanical energy of the system is not a constant. Okay, so that's because the collision is inelastic. Now part D, at what angular speed does the door swing open immediately after the collision? So I think of the system, is bullet plus door, and for this system, do I have any external torque acting on the system with respect to the hinge? The net external torque acting on the system for rotations about an axis going through the hinge will be 0. Therefore, the total angular momentum must be conserved. All right. So let me think about what will be the final angular momentum of this system. Well, because I have a rigid object, the door, it's going to have an angular momentum I omega final for the door, and for the bullet I will have a arc cross width mv. So this is going to have L minus R mass times omega final times L minus R. So that will be the final tangential speed after the collision. So I'm going to find that the final angular momentum will be the moment of inertia of this door with respect to its end point for rotations around the end point. We know this for a rod, so that's going to be 1/3 m, capital M, the mass of the door, L squared, multiplied with omega final, plus m L minus R squared omega final. So I can calculate this final angular momentum. If I plug in the numbers, this will be 1/3. The mass of the door is 18 kilograms times 1 squared, that's the length of the door, times omega final, plus a mass of the bullet 0.005 kilograms times 0.9 meters squared times omega final. Alright, so the final angular momentum here is 18 divided by 3. It is 6 omega final plus 0.005 times 0.9 squared omega final. This must be equal to omega, the L initial, because L final must be equal to L initial, which we have calculated. It is 4.5 kilograms meter per second square in k-hat direction. So I find that omega final should be equal to 4.5 divided by 6 point 004 0.5 is what I have here. So well, we can calculate this. 0.9 squared is 0.81. So multiplied with 0.005, it will give me 0.00405. Okay, so the answer is 0.749 radians per second, and this is going to be in k-hat direction. So the final angular speed will be 0.0749 radians per second in k-hat direction. Now in part E of the problem, so I have some space left here, so let's calculate part E here. Calculate the total energy of the bullet door system, determine whether it's less than or equal to the kinetic energy of the bullet before collision. The final kinetic energy of the bullet door system will be 1/2 moment of inertia of the door omega squared plus 1/2 for the bullet. I can think of this as a particle, mass of the bullet L minus R squared, that's the moment of inertia, omega squared. So if you do this calculation, you find the final kinetic energy will be 1 over 2 1/3 ml squared, so it's 18 times 1 squared, omega final squared, 0.749 squared, plus I have 1 over 2 mass of the bullet 0.005, and then I have 0.9 squared, 0.749 squared. The final kinetic energy I calculate here to be 1.68 joules. The initial kinetic energy, on the other hand, is 1 over 2 mass of the bullet, its velocity squared, and if you calculate this, it's 1 over 2 0.005 times 10 to 6. This is going to give me 2.5 times 10 to 3 joules. So I can see that my final kinetic energy 1.68 joules, my initial kinetic energy 2.5 10 to 3 joules. So final kinetic energy is less than the initial kinetic energy. So K final is less than K initial. There is a lot of energy loss in the system during this collision. Now I want to try something to calculate this omega final again and ask you if this approach has any problems. So let's think about a different way of calculating omega, if it's possible. My question is, during the collision, is linear momentum conserved? So normally we say if an object gets embedded into the other object that it hits, it's perfectly inelastic collision and linear momentum must be conserved. So let's remember what is the condition for this linear momentum to be conserved here. Net force, net external force, x component must be equal to 0 so that I will have the change in the x component of linear momentum to be 0, because remember, net external force is equal to dp dt. So my question is that the case here? So let me concentrate on this situation. So I look at the bullet door system and try to find if there is an external force with an x component that acts on the system so that the linear momentum would not be conserved. So if I try to write linear momentum conservation, I would say initially I have a linear momentum mv, and finally I should have a linear momentum capital M omega final times L over 2, because this is the center of mass here and this is at a distance L over 2 from the side. So I would have a tangential velocity V final would be equal to omega final times L over 2 from the rotation. Right. So that would be the x component of the linear momentum from the door, and then I would have, because the bullet is embedded inside, I would have mass times omega final times L minus R as the final linear momentum, and then I would equate these two. So I leave to you as an exercise, if you equate these two, you will find that omega final that you get from this calculation will not be the same omega final that I'm getting here. And why is that? Because if you really think about this carefully, when you have this impulse coming from this collision, so I have this impulse here, there is a force being applied for a certain period of time. What will end up happening is that the hinge will create a reaction force. Okay? So the reason it doesn't work, the reaction force at the hinge is an external force for the bullet door system.